Hi, my name is Brianna Poon, and this is my report for Lab 4, Oscillations in Physics 2211. So the purpose of this lab is to analyze the motion of a mass swinging in an arc while oscillating on a spring. And to do this, I used a tracker software to digitally analyze the motion of a mass through a video, and then created a computational model and plotted both the predicted and observed data and compared the two. So some fundamental principles I use are Newton's second law, which states that a net force on an object is equal to change in momentum over change in time. And then from that, I also have the velocity and position update formulas. And then I also use the energy principle, which states that changing energy in a system is equal to work done by the surroundings, plus an exchange of thermal energy between the system and surroundings. So the three types of energies that I considered in this lab are kinetic energy, spring potential energy, and gravitational potential energy. So my procedure involved analyzing a video of a swinging and oscillating mass through tracker, where my system was the mass, the spring, and earth, and the surroundings were nothing. And then using the initial conditions from tracker, I created a computational model and then graphed data from the two and compared those graphs. And then my assumptions were that since nothing is in the surroundings, I could use spring and gravitational potential energies and assume that work is equal to 0 and thermal energy is equal to 0, and therefore that the change in total energy is equal to 0. So here is a brief video of my tracker analysis. And then the data that I got from that are the initial conditions, like the position, the velocity, start time, end time, and delta t. This delta t was determined from the frame rate of the video. And then I also had some predetermined data, since this wasn't a video that I took on my own. The mass was 0.402 grams, the spring constant was 0.683, and the relaxed length of the spring was 0.123 meters. And then I inputted those in my code. On the left-hand side, I have the constants here, and then I also calculated the L hat vector and S for the calculation of spring potential energy, and then I also calculated gravitational potential energy and kinetic energy, and then added all three of those for the total energy. And on the right hand here is the actual iteration process where I calculated gravitational force and then spring force, and then added those two to get the net force, and then used that net force to apply the momentum principle and update velocity and position. And then finally, I updated the spring since the length of the spring is changing as it's oscillating, and then also calculated the energy changes. So here are the graphs that resulted from my code. The big one on the left shows all of the different energies plotted, as well as the total change in energy. And then on the right, I have the x position versus time and y position versus time for the model, my computational model, and then also my experimental data. So as you could see on the previous slide, the changes in potential energy for spring energy and gravitational energy and kinetic energy, they all oscillated, but in a manner that resulted in a constant delta E equals 0. And I'll discuss this further on the next slide, but this proves that the law of conservation of energy is supported. So my x position versus time graph shows that the model is fairly accurate in its prediction of position along the x-axis, but for the y position versus time graph, it was a little more variable, which indicated that there may have been other forces or energies that I did not account for. So some sources of error here are not accounting for things like drag force or change in thermal energy, which could probably help account for variability in the y-axis position predictions. And then also I manually inputted the center of mass points in tracker, which could have been a source of error as well. So is the energy principle satisfied? As I mentioned previously, yes, it is satisfied because though the individual energies fluctuate, the total sum of energy always remains at a constant 0. So also I estimated the oscillation periods for the x and y position data, and I did this by measuring the change in t between the crest and the sinusoidal x and y position graphs in tracker and then taking the average. So for the x position data, that was 1.6334 seconds, and for the y position data, it was 1.5037 seconds. And so the difference in these periods of oscillation can be explained by things that I didn't consider, such as like the drag force and also my inaccuracy in like tracking the center of mass. And this difference could impact the value of the spring constant because, as you can see, I put the equation for oscillation period up here. This k is the value of the spring constant, and so because that value is affected, it could also therefore impact like the magnitude of the spring force and the spring potential energy. So that is the end of my report, and thank you for listening.